Here we're introducing a new family of trigonometric identities. These are called the double angle identities, or the double angle formulae. The first of them is that the sine of 2a is identical to 2 times the sine of a times the cos of a. We can demonstrate this works with an example. For example, the sine of 60 degrees should be equal to 2 times the sine of 30 degrees times the cosine of 30 degrees. Here we have a is equal to 30 degrees, and therefore 2a is equal to 60 degrees. We know the exact values. We should know that sine 60 degrees is equal to root 3 over 2. And evaluating the right-hand side, 2 times sine 30 times cos 30 will be 2 times sine 30, which is a half, times cos 30, which is root 3 over 2. The 2's cancel, giving us root 3 over 2. So we can demonstrate that this formula works with this example. However, the proof of this first formula is left as an example for you to do. It's done in exactly the same way, however, as the cos 2a formulae, the first of which is it's identical to cos squared a minus sine squared a. This is also identical to 2 cos squared a minus 1, which is also identical to 1 minus 2 sine squared a. We're going to prove these here. Cos a plus b, we know, is cos a times cos b minus sine a times sine b. This is one of our compound angle formulae. If we let b be equal to a, which we can do since the identity means that it should work with any angle, and we get cos a plus a is identical to cos a times cos a minus sine a times sine a. A plus a is 2a. Cos a times cos a is cos squared a. And sine a times sine a is sine squared a. We can use this to get the second version. Here we use the Pythagorean identity, cos squared theta plus sine squared theta is identical to 1. This can be rearranged to give us that sine squared theta is identical to 1 minus cos squared theta. We use this to substitute here. So cos 2a is going to be cos squared a. Take away 1 minus cos squared a. So we've just replaced the sine squared a. Expanding the bracket, we get cos squared a, take away 1 plus cos squared a, which is 2 cos squared a minus 1. We can use this again, but this time rearranged to give cos squared theta is the same as 1 minus sine squared theta, to substitute in here. So our cos 2a is 1 minus sine squared a. Take away sine squared a. This is 1 minus sine squared a minus sine squared a, which is 1 minus 2 sine squared a. The tan 2a formula is also left as an exercise, but both the sine 2a and tan 2a formulae are produced by the corresponding a plus b formulae, with b replaced by a, in exactly the way as we proved cos 2a was identical to cos squared a minus sine squared a.